Ashkezari. I'm a principal research scientist at the University of Washington in Seattle. Uh, I'm also the project lead for CMAP, which I'm presenting today. So let me just jump right in with a simple definition. What is Simon CMAP? Um, the database of ocean data set, a how nice database of ocean data set. Um, but one of the main sort of goals of the project is to really simplify the process of integrating data sets, a sort of large amount of heterogeneous ocean data sets with each other. And the way we achieve this is closely connected to the inner workings and architecture of Simon CMAP. Everything starts with collecting data. We get data from mainly our collaborators. These are funded by Simons Foundation, about 30 international institutions and universities. We also get data from public repositories. We turn this data into a unifying data format. It's very simple. I'll show you in a second. We also add consistent and rich metadata layer on top of each data set. Both of them are pretty important in terms of data integration service, which I'm going to talk about mainly. Once data is ready, you push them into a database system. Also, a copy of the data is also submitted to registered repositories to get an UI for long-term care. Database is the key component of our architecture because obviously it holds data, but also it holds certain important functions that are responsible for low-level and efficient data operations. Things like efficient query, like search, or data slicing, or analytics like aggregation. And so because these functions are written in a low-level language and embedded into the database layer, it means any programming language can invoke these functions and get the data back. And in that sense, CMAP is programming language agnostic. And then there's an API, this is like a standard web API on top of the database, the RESTful API. Essentially, it's a gateway to the data layer. And then we have applications on top. So there's a web app, a website, as well as a number of programming languages, Python, R, and massive engineer. Now, in terms of content, we have data from all sectors, satellites, as well as institute, and you have massive numerical model outputs. These are some example data sets. As I said, they're coming from various sources. The point being, we push them all, we turn them all into a unifying, very simple unifying data model, which guarantees that every single data point has time and location annotations in a consistent format. And we index them for efficiency and for integration purposes. And of course, every data set can have its own variable. Data sets are stored in so-called table objects, which means if you want to get any data set, doesn't matter which type of data set it is, you only need to know the corresponding table name. This under the bottom here, we're looking at like a Python snippet of our of Simon CMAP to get, for example, a slice of Armbrust. Now, if you want to integrate two very different data sets with each other, this is a sort of illustration of say two different. So let's say you have like a cruise trajectory, and you want to integrate that with satellite temperature. So you want to get like satellite essentially a long track of a cruise. You can do that in CMAP again, and the snippet at the right-hand side. You only need to pass the table names to that function, and you would only define, essentially need to define to how flexible you are when you want to match these two data sets with each other, and that's it. Everything else will be handled in the back end where the data is. So there's no type of data between client and the server. So it's completely independent of the type of data set that one integrate. Any type of data set can handle that. Okay, so we have used this service for several research studies already with a few examples. On the left-hand side, we're looking at a model, the neural network model that we trained for certain important cyanobacteria. So this is the model to essentially predict the distributions of cyanobacteria at the global scale. And the way we do it is that we first compile decades of about 4 decades of direct measurement of these cyanobacteria abundances. Then we train the model. The way we train it is we use predictors, and those predictors are contemporaneous environmental parameters. Those contemporaneous environmental parameters are coming from various different data sources, which we use the data integration to do that. That's practically impossible to do such studies on single machine or even single server. It's just the amount of data is so massive. On the right-hand side, I have only 1 minute, I guess, I'm gonna skip. On the right-hand side is, again, another model. This is a convolutional neural network where we trained a CNN model to classify images. These are images coming from various different imaging devices, both plankton and phytoplankton. Okay, quickly, conclusions. If you really want to maximize our understanding of the ocean data sets, they're growing really fast, obviously. We think it's important to be able to blend them together. And if you want to do that, it's important to invest on such sort of data integration service. One thing obviously we learned was that if we want to build this type of integration services, it's really important to focus on creating rich and consistent data and metadata data models. Yeah, thank you.